Hello, everybody. This problem isn't from any particular contest, but it's certainly the sort of problem that could be on a contest. In fact, it's a very similar to setup to problem A1 from the 2020 Putnam exam, which I just posted a video about a few weeks ago. So I want to show you how you might approach this problem and also point out that this number 317 ultimately in the end is completely irrelevant, which is a little bit surprising. So let's look into this problem. So first, we're trying to find a number which is of this form. So of course, parsing this is the first trick. It says you have some number of ones followed by some number of zeros. So we don't know how many ones, how many zeros, but examples of numbers of this form might be 1, 1, 0, 0, 0, right? It has two ones and then three zeros. Or you might have 1, 1, 1, 1, 1, 0. So that's got five ones and one zero, or maybe even just like 111, right? That's got three ones and no zeros. And we want to know whether or not there is going to be a number of this form which is divisible by 317, which is actually maybe surprising that such a thing is going to exist. 317 doesn't really look like it should go into these sort of numbers, but you know what? Sometimes we get surprised in math. So we're going to handle this using modular arithmetic, and this is the one place where 317 will come into play. And the way we're going to do this is by making the following observation first, which is that numbers of the form ones followed by a bunch of zeros, so any number of the desired form, so of the form bunch of ones, and we'll say you have m of them followed by a bunch of zeros, you have n of them, equals, well, what you could do is take m plus n ones. So just take the number that's all ones and then subtract the number which is n copies of 1. Right? Because when you subtract these, okay, the last n digits are going to go away and you'll just get zeros, and the first m digits are still going to be ones. All right, so what we're really then asking for is numbers n and m such that when you build this number, m plus n copies of 1, and you subtract this number, n copies of 1, you get a number which is divisible by 317. Now, if we work in modular arithmetic, so we're going to work modulo 317. So what we want is m and n such that 317 divides m plus n ones minus n ones. And as I said, we want to move into mod 317 arithmetic. This is equivalent to stating that m plus n copies of 1 is congruent to n copies of 1 mod 317. Okay, or I mean, actually the intermediate step, which is actually very useful here, that if you subtract n copies of 1 from m plus n copies of 1, that this is congruent to 0 mod 317. All right, so we've changed the problem, right, from finding some ones and zeros such that it's divisible by 317 into finding basically two different numbers which are just of the form 1, 1, 1, 1, 1, and showing that they're the same modulo 317. Okay, so either way, like we can use either one of these. Well, let's say we started writing down the possibilities. Okay, so I have 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, so forth. Okay, and I keep going, dot, dot, dot. And I'm going to stop when I get to 318 copies of 1, right? Now, of course, I didn't choose 318 randomly. This is 317 plus 1. And what I know is that each one of these I could reduce modulo 317. Oops, let's try that again. Modulo 317. And when I do, I'm going to get some residue, right? We'll call this maybe R1, and this could be R2, and R3, and R4, and R5, and so forth. And this last one will be R318. And when I do this, I can always choose my residues so that they're what Gauss would have called the least positive residues, although that also includes 0. So they'll be in the numbers 0, 1 through 316, excuse me. All right. So if you like, you can think about this as, hey, you divide by 317, what's the remainder? And you can always take the remainder to be some number between 0 and 316. Okay, but now I have 318 elements, right? These remainders, 318 remainders or residues. And they live inside of a set, which, okay, it looks like there's 316 elements, but don't forget the 0. There are 317 elements. And so by the pigeonhole principle, we know there must be a repetition. So by the pigeonhole principle, we say there exist, let's call it, how about N and L, such that R sub N is equal to R sub L. And let's assume, just for sake of argument, that the L is the bigger of the two. Okay? So there has to be two of these that are actually the same. Well, what that tells us is that if I do L copies of 1 and I do N copies of 1, since these have the same remainder mod 317, this is 0 mod 317. And so, of course, since L is greater than N, I can write this as N plus some number. Maybe we'll call that M. And these are going to be the N and M that I'm looking for. So it follows that if I take M copies of 1, and I then take N copies of 0, that this is congruent to 0 mod 317. Because this down here is that difference, right? I've pulled off the N copies of 1 from the end, and I still have M copies of 1 at the beginning. All right, so using modular arithmetic and the pigeonhole principle, without actually doing a single division, we are able to show that there's going to exist some number of this form, which is divisible by 317. Now, note this is an existence proof. This does not actually construct the value explicitly in the sense we don't know what it is. Now we could like go into a spreadsheet, all right, or into Python or something, right? And we could just say, all right, let's test which of these ones, right, are going. What are the two smallest which have the same residue, and then we'd be able to get an answer. Now, what is quite surprising, because I actually did run this through, well, it wasn't the spreadsheet, I actually used the programming language GAP. And what's an amazing surprise, of course, none of this proof is needed to show this, right? Like, this is just trivia here. If you take 79 ones in a row, that actually is divisible by 317. So the first repeat, at least that my eyes were able to find, didn't even occur where you had two sets of ones with the same remainder, but actually occurred when the remainder was 0. And so you could actually just immediately write this down. So you didn't even need to have any zeros on the end. So it might be that in the list I missed some pairs that matched off. That's very likely. I was just eyeballing it. So if you can find a couple of pairs which are even smaller, I would love to hear about that in the comments. All right. Take care. Bye-bye now.